40 trillion kilometers ago, on an ordinary afternoon in human history, someone looked up at the sky and decided the stars were reachable. The math says otherwise. Proxima Centauri sits 4.2 light-years from the Sun, Barnard's star at 6, Sirius at 8.6. To cross even the first of those gaps, a human body would have to survive what no human body has ever survived. What waits in that dark is stranger than the dark itself. Tonight, we are going to travel outward from the last warm edge of our solar system, through the interstellar void, past the churning red eye of Proxima Centauri, and onward toward the bright shoulder of Sirius, and understand why the distance between stars is not just a number, but a condition. Before we dive in, if you love exploring the cosmos as much as we do, take a second to like the video or subscribe, and tell me where you're listening from and what time it is. Now, let's begin. Picture yourself standing outside on a clear night, away from the cities, somewhere dark enough that the sky does its full work. The stars do not look far. That is the first deception. They appear close enough to name, close enough to navigate by, close enough that for the majority of human history, virtually every civilization on Earth believed they were embedded in a sphere just overhead, a fixed canopy, rotating, near. The ancient Greeks measured the universe in stadium lengths and found it comfortably sized. The medieval scholars placed the stars in crystalline shells, each nested inside the other like a set of spheres, the outermost only a modest distance from the hand of God. Even the most daring cosmological thinkers of the Renaissance, the ones who argued that the Earth moved, still imagined the stars as relatively nearby. They were wrong. They were wrong in a way that still has not fully registered in the human gut, despite 4 centuries of trying. The true reckoning began in the early 19th century, in the careful hands of a German astronomer named Friedrich Wilhelm Bessel. In 1838, working from the Königsberg Observatory in what is now Kaliningrad, Russia, Bessel succeeded in measuring the parallax of a star called 61 Cygni, the tiny apparent shift in a nearby star's position against the background of more distant stars, as Earth moves from one side of its orbit to the other. It was an extraordinary achievement of patience and precision, the culmination of years of nightly measurements made with a heliometer, an instrument designed to split starlight and compare angles to fractions of an arc-second. What Bessel found, after all that care, was that 61 Cygni was roughly 10 light-years away. A light-year, the distance light travels in a vacuum in 1 year, amounts to approximately 9.46 trillion kilometers. So 61 Cygni sat about 94 trillion kilometers from Earth. Bessel understood, perhaps more viscerally than anyone before him, what that number meant. The universe had become enormous on a single evening of calculation. That same year, the Scottish astronomer Thomas Henderson, working from earlier observations he had made at the Cape of Good Hope in South Africa, announced his own parallax measurement of Alpha Centauri, our nearest stellar neighbor system. Henderson had actually made his observations first, in 1832 and 1833, but had hesitated to publish, fearing the measurements would be disbelieved. When Bessel's announcement forced his hand, Henderson confirmed what his own numbers had been quietly telling him. Alpha Centauri was about 4 light-years away, closer than 61 Cygni, the nearest star anyone had ever measured. And still, 4 light-years, still, roughly 38 trillion kilometers. Pause here for a moment and feel the weight of those early measurements. These men were using angles smaller than a fraction of 1/1000th of a degree, the angular equivalent of seeing a human hair from 10 meters away, and what they found What their painstaking mathematics revealed was that even the nearest star was so far removed from us that light itself, traveling at nearly 300,000 kilometers per second, needed more than 4 years to complete the journey. They had not found comfort in the measurement. They had found a vast and indifferent emptiness. Now we have a much clearer picture, assembled over nearly 2 centuries of increasingly refined measurements, most recently from the European Space Agency's Gaia spacecraft, which between 2013 and 2022 mapped the positions and distances of nearly 2 billion stars with extraordinary precision. What the full catalogue tells us is this: our nearest stellar neighbours form a small, rather diverse community spread across a volume of space roughly 20 light-years in radius. Proxima Centauri, a dim red dwarf, is the closest at 4.244 light-years. Alpha Centauri A and B, a pair of sun-like stars locked in a mutual orbit, sit just slightly farther, at approximately 4.37 light-years. Barnard's star, a red dwarf discovered to be remarkable in 1916 by the American astronomer Edward Emerson Barnard, who found it moving faster across the sky than any other known star, lies at 5.96 light-years. Then there is Sirius, the brightest star in the night sky, a system of 2 stars located 8.6 light-years away, glittering blue-white in the constellation Canis Major. These are our neighbours. These are the closest suns to our own in the entire galaxy, and every single one of them is an almost incomprehensible distance away. Something deserves attention here before we go any further. 4 questions have been quietly waiting since the moment this journey began. One of them will not be answered until near the very end of what lies ahead, and it is the most important of all. It is simply this: will we ever actually go? Not in the abstract, aspirational sense of science fiction, but in the physical, material engineering sense. Will any human being, or any probe built by human hands, ever cross the interstellar gulf and arrive at another star? That question sits at the edge of everything we are about to explore, and it will stay open, like a door ajar in a dark hallway, for a long time yet. A second question, slightly smaller, but still immense: what would the journey actually do to a human body? We know, in rough terms, what the interstellar environment contains, but we do not fully understand what months or years of crossing it would feel like from inside a body of bone and blood and nerve. That question will take several sections to even approach. A third question, answerable within the span of a few hours of narration: what waits at the destination? Proxima Centauri has a planet, confirmed in 2016 by astronomer Guillaume Anglada-Escudé and his team, using years of radial velocity data gathered at the European Southern Observatory. That planet, Proxima Centauri b, orbits within what astronomers call the habitable zone, the range of distances from a star where liquid water could theoretically exist on a surface. But whether it is habitable in any meaningful sense is a question whose answer, when it comes, will both satisfy and trouble you. And a fourth question, the smallest, the most immediate, the one that will be answered first: what is the interstellar medium actually made of? What fills the space between the stars? Most people, if pressed, would say nothing. The answer is more interesting and more dangerous than nothing. These 4 questions: will we go? What would it do to us? What waits there? And what fills the void between? Are the architecture of everything ahead. Hold them gently. The spatial journey we are about to make follows a single, continuous outward path. We begin at the edge of our solar system, in a region called the heliosphere, the vast bubble of solar wind and magnetic influence blown outward by our Sun. We move through the heliopause, the boundary where the Sun's influence ends and interstellar space formally begins. We cross the interstellar medium, that tenuous, radiation-soaked, dust-threaded near vacuum that separates the stars. We approach Proxima Centauri and examine it closely before pressing onward to Alpha Centauri A and B, then curving outward toward Barnard's star, and finally reaching the blue brilliance of Sirius. At each stop, we will ask, what is here? What does it mean? And could anything made of human biology survive the crossing? Before that journey begins in earnest, one more foundation must be laid. The distances themselves, not as abstractions, but as lived physical realities that resist every analogy we try to throw at them. The fastest human-made object in history, as of this writing, is the Parker Solar Probe, which in late 2024 achieved a speed of approximately 692,000 kilometers per hour at its closest approach to the Sun, having used repeated gravity assists from Venus to tighten its orbit. That speed is extraordinary by any terrestrial standard. It is over 192 kilometers per second. It is the kind of speed that makes the human mind reach for poetry. And yet, at that velocity, the fastest anything built by human hands has ever traveled. The journey to Proxima Centauri would take roughly 6,300 years. A civilization would rise and fall in the transit time. The ancient Egyptians began constructing the pyramids at Giza approximately 4,500 years ago. Parker, at its fastest, would still need another 1,800 years after that to arrive. The more frequently cited interstellar benchmark is Voyager 1, which NASA launched in September 1977, and which, as of 2024, has traveled approximately 24 billion kilometers from Earth, further from the Sun than any human artifact in history. Voyager moves at about 17 kilometers per second, which sounds fast until you understand that it would take this probe approximately 73,000 years to reach Proxima Centauri if it were aimed in that direction, which it is not. Voyager 1 is heading toward the constellation Ophiuchus, and in about 40,000 years will pass within 1.6 light-years of Gliese 445, a star in the constellation Camelopardalis. By the time it would hypothetically arrive at our nearest neighbor, our Sun will have aged by nearly 1% of its total lifespan. Civilizations built in stone will have dissolved. Languages will have evolved beyond recognition tens of thousands of times over. These numbers are not shared to overwhelm, but to calibrate. What lies ahead in this exploration demands that you carry the distances not as abstractions, but as physical facts felt somewhere below the sternum. The stars are not far in the way that a city on the other side of a continent is far. They are not far in the way that the moon is far, or even Mars. They exist at a remove that is, by any reasonable biological reckoning, absolute. And yet, here we are, at the beginning of a journey, because the question of whether that distance can be crossed by probes, by signals, or someday by people is one of the most consequential questions our species has ever asked. One last piece of the foundation before we step through the door. Our solar system is not simply the Sun and the 8 planets. It extends in the form of the Sun's gravitational and electromagnetic reach much farther outward than most maps suggest. The region dominated by the solar wind, the continuous stream of charged particles flowing outward from the Sun, is called the heliosphere. The boundary where that solar wind finally loses the battle against the pressure of interstellar space is called the heliopause. Voyager 1 crossed the heliopause in August 2012, confirmed by a team led by physicist Edward Stone of the California Institute of Technology, who announced in 2013 that the probe had entered interstellar space. Even then, even after 35 years of travel, Voyager was only at the inner edge of the true interstellar gulf. Beyond the heliopause lies the Oort cloud, a vast spherical halo of icy objects extending perhaps 1 to 2 light-years from the Sun, still gravitationally bound to our star, still technically within our solar system in some formal sense. Truly leaving, entering the space between stars, free of any solar gravitational anchor, requires traveling beyond even the Oort cloud. That crossing point, roughly 1 to 2 light-years from Earth, is where this journey formally begins. And it begins in silence, and in a cold that has no parallel in any earthly experience. The Oort cloud deserves a moment of genuine attention before we pass through it, because it is one of the stranger features of our solar system, and one of the least appreciated. Formally proposed by the Dutch astronomer Jan Oort in 1950, based on his statistical analysis of long-period comets, this spherical shell of icy bodies begins somewhere around 2,000 astronomical units from the Sun, an astronomical unit being the average distance from Earth to the Sun, about 150 million kilometers, and extends outward, by most estimates, to somewhere between 50,000 and 200,000 astronomical units. In light years, the outer edge of the Oort cloud sits somewhere between 1 and 2 light-years from the Sun, roughly halfway, in other words, to Proxima Centauri. The Oort cloud has never been directly observed. Not a single object within it has been imaged. Its existence is inferred entirely from the orbits of comets that occasionally fall inward toward the Sun, nudged by the gravitational influence of passing stars or the tidal pull of the Milky Way's disk, and from the mathematics of orbital mechanics. Jan Oort looked at the distribution of cometary orbits in 1950 and reasoned backward, the way a detective reasons from footprints to the structure that must be generating them. What he found, or rather what he deduced, was a halo of perhaps hundreds of billions of icy bodies loosely bound to the Sun, occupying a shell of space so large it begins to blur the boundary between our solar system and interstellar space. Here is what that means practically. Even if you could leave Earth tomorrow, traveling at the fastest speed any human artifact has ever achieved, you would spend thousands of years just crossing our own solar system's outermost envelope before entering the true interstellar gulf. The stars are not simply far away. They are separated from us by a distance that begins with tens of thousands of years of travel just to reach the exit door. Beyond the Oort cloud, beyond the last wisp of solar influence, the Sun shrinks to just another star among many. Bright, certainly, prominent in the sky of any nearby stellar system, but no longer home, no longer anchor. The Sun becomes a point of light. What surrounds that point of light in every direction is what we must understand before the journey can proceed honestly. It is not empty. It has never been empty. It is filled with something that will kill you in ways you have not yet imagined. Take a moment to look back at where we stand. We have established the distances. We have felt, in some measure, the inadequacy of every vehicle humanity has built. We have planted 4 questions that will need answers before this journey is done. Now the path opens outward, and the first section of it runs through the strangest boundary our solar system possesses, the place where the Sun stops being the Sun and space becomes something else entirely. We are leaving home, and home, it turns out, is a much smaller place than we thought. The heliosphere is, at its simplest, a bubble. The Sun continuously exhales. This is not a metaphor but a physical process, streaming charged particles outward in all directions at speeds ranging from about 400 to 800 kilometers per second. This outflow, called the solar wind, carries with it the sun's own magnetic field, stretched and wound as the sun rotates, threading through the entire volume of the inner solar system like invisible wire through a vast room. The solar wind does not stop at Pluto, does not stop at the edge of the Kuiper belt. It continues outward, thinning gradually, weakening, until it finally loses the pressure contest against the interstellar medium, the gas and dust that fills the space between stars. At that boundary, the solar wind slows abruptly in a standing shockwave called the termination shock, then dribbles forward into a turbulent mixing zone called the heliosheath, before finally giving up entirely at the heliopause. Stand at the heliopause, if you can place yourself there in imagination. The sun behind you is no longer the eye-filling disk of your childhood. It is a bright point, the brightest star in your sky by far, but a point. Its light, arriving at this distance, somewhere around 121 astronomical units in the direction Voyager 1 traveled, has taken roughly 17 hours to reach you. The solar wind is barely a whisper. The temperature of the solar wind particles, which near the sun's corona is measured in millions of degrees, a consequence of how the sun heats its outer atmosphere, has dropped to something in the range of tens of thousands of degrees in the heliosheath, though the density has also dropped to the point where this temperature would not warm your hand. Temperature and heat are not the same thing. You can have particles moving with extraordinary kinetic energy while so few of them exist that they transfer almost no warmth to anything they encounter. What Voyager 1 told us, after it crossed the heliopause in 2012, the crossing confirmed by Don Gurnett of the University of Iowa and the Voyager team led by Edward Stone at the California Institute of Technology, who announced their analysis in September 2013, was both confirming and surprising. The probe's instruments detected a sudden increase in galactic cosmic rays, high-energy particles accelerated by supernova remnants, and other violent processes elsewhere in the galaxy, which had been partially blocked by the solar wind's magnetic bubble. The density of the plasma around the probe changed. The direction of the magnetic field shifted. These were the signatures of interstellar space. The universe beyond the sun's breath had touched the probe's instruments. But here is what made the scientists at the Jet Propulsion Laboratory in Pasadena pause. The magnetic field direction at the boundary was not quite what the standard models predicted. Some researchers had expected a sharper, cleaner transition. Others had predicted specific orientations of the interstellar magnetic field that did not quite match what Voyager found. The heliopause, it turns out, is not a simple wall. It is a dynamic, shifting, complex membrane, breathing slightly with the sun's own 11-year activity cycle, shaped by the relative motion of our solar system through the local interstellar medium. It is a boundary, but a living one. The solar system moves through the galaxy at approximately 220 kilometers per second, orbiting the Milky Way's center. As it moves, the heliosphere is compressed slightly on the leading edge, the nose of the bubble in the direction of motion, and stretched into a long tail behind, sometimes called the heliotail. Voyager 1 crossed through the nose region. Voyager 2 launched 16 days before Voyager 1 in 1977 and traveling in a different direction, crossed the heliopause in November 2018 and found a slightly different thickness and character to the heliosheath on its side, confirming that the bubble is not symmetrical, not uniform, not simple. Both probes are now in interstellar space. Both are functional, though only barely. Voyager 1 carries its plutonium-powered generators, decaying slowly, its transmitter signal arriving at Earth so weakened by distance that it requires the largest radio dishes on the planet to detect it. By the mid-2030s, the power budget will fall below the level needed to operate any scientific instrument. The probes will go dark, still traveling outward, still crossing the interstellar medium in silence for millions of years to come. This is worth pausing on. Voyager 1 will continue its journey through interstellar space long after the civilization that built it has transformed beyond recognition or ended entirely. In roughly 40,000 years, it will pass within 1.6 light-years of a dim red dwarf star called Gliese 445, never stopping, never slowing, carrying a golden record containing sounds and images of a civilization that may no longer exist in any form its own creators would recognize. The probe will outlast us. The universe, indifferent, will not notice. Beyond the heliopause, the interstellar medium begins. This is the substance of the void, the material that fills the space between stars, the environment that any interstellar traveler must cross. Most people, if asked, would say that space is empty. The textbook image of interstellar space is a perfect vacuum, featureless, cold, a nullity. That picture is almost entirely wrong, or at least it is a vast oversimplification that collapses the moment you look at it more carefully. The interstellar medium is composed primarily of hydrogen and helium, the two most abundant elements in the universe, the raw ingredients from which stars themselves are built. But it also contains trace amounts of heavier elements, complex molecules, polycyclic aromatic hydrocarbons, water ice, silicate dust grains, carbon compounds. It is riddled with magnetic fields, threaded with streams of high-energy cosmic ray particles, bathed in radiation from distant stars and supernova, and the faint glow of the cosmic microwave background. It is structured. It has phases, regions of wildly different temperature and density coexisting in a kind of rough pressure equilibrium. The cold neutral medium, found in dense clouds, sits at temperatures around 50 to 100 Kelvin, roughly minus 220 degrees Celsius, with densities of perhaps 20 to 50 hydrogen atoms per cubic centimeter. The warm neutral medium, in the more diffuse regions between clouds, sits at 6,000 to 10,000 Kelvin, with much lower densities. And then there is the hot ionized medium, plasma heated by supernova shockwaves to temperatures of 1 million Kelvin or more, with densities sometimes as low as a fraction of an atom per cubic centimeter. Our solar system sits inside a particularly unusual region of this medium. Sometime between 10 and 20 million years ago, a series of supernova explosions in our galactic neighborhood excavated a vast cavity in the interstellar medium, a region roughly 1,000 light-years across, filled with hot, thin, ionized plasma. This cavity is called the local bubble, and our solar system is near its center, drifting through some of the least dense and most peculiarly structured interstellar material in the immediate galaxy. The astronomer Rosine Lallemant and colleagues, using data from the ESA's Hipparcos satellite and later Gaia, have refined our understanding of the local bubble's shape and boundaries considerably over the past 2 decades. What they have found is a complex, irregular structure with walls of cold, neutral material formed where supernova blast waves have compressed the interstellar medium into dense shells. For a hypothetical interstellar traveler, the local bubble is simultaneously good news and bad news. The good news is that the hot ionized medium is tenuous enough that dust grain collisions at high speed are somewhat less frequent than they would be in a denser molecular cloud. The bad news is that the hot medium is soaked in galactic cosmic rays, high-energy protons, alpha particles and heavier nuclei accelerated to fractions of the speed of light by supernova remnants and other violent astrophysical accelerators. Within our heliosphere, the Sun's magnetic field provides partial shielding, deflecting many of these particles before they reach Earth. Beyond the heliopause, that shield is gone. A traveler, or a probe, crossing the interstellar medium is exposed to the full unattenuated flux of galactic cosmic radiation. A flux that, over the timescales relevant to any credible interstellar journey, would deliver doses of ionizing radiation far beyond what any current shielding design could absorb. The fourth question, what fills the void, now has its answer, and the answer is not reassuring. The interstellar medium is not nothing. It is a complex, hostile, structured environment that will erode unshielded surfaces, scramble unprotected electronics, and deposit lethal radiation doses in unprotected biological tissue. It is not a vacuum into which you can sail cleanly. It is a medium that pushes back. Consider what this means at speed. Any probe or vessel crossing the interstellar medium at a significant fraction of the speed of light, say 20%, the target speed of the breakthrough starshot concept, would encounter the interstellar medium not as a sparse, leisurely drift through occasional atoms, but as a violent particle bombardment. At 20% of light speed, even a single hydrogen atom strikes the leading surface with the energy of a high-velocity rifle bullet. The interstellar medium, at that speed, becomes a sandblaster operating at energies that no conventional material absorbs gracefully. Each square centimeter of frontal cross-section would collide at high speed with roughly 1,000 particles of size at least 0.1 micrometers. And that is for a craft moving at the speed Starshot envisioned, a calculation that gave the engineers considerable pause. This is where the problem of propulsion meets the problem of survival, and they collide badly. To cross the interstellar distance in any time frame shorter than geological, a vehicle must travel at a substantial fraction of light speed. But at those speeds, the interstellar medium becomes a wall of physical violence. The engineering must solve both problems simultaneously: how to go fast enough and how to survive going that fast. No one has solved either of them completely, and the closer you look at the proposals that have been offered, the more the difficulty deepens. The honest catalogue of interstellar propulsion concepts is both inspiring and sobering. Chemical rockets, the technology that took humans to the moon and sends probes throughout the solar system, are simply out of the question for interstellar travel. The fundamental limit here is the rocket equation, formulated by Konstantin Tsiolkovsky in 1903. To accelerate a spacecraft to even 1% of the speed of light using chemical propellants, the mass of fuel required would exceed the mass of the observable universe. This is not an exaggeration. It is the inescapable mathematics of exhaust velocity. Chemical rockets achieve exhaust velocities of perhaps 4 to 5 kilometers per second. Light speed is roughly 300,000 kilometers per second. The ratio between them makes chemical propulsion irrelevant for interstellar travel, in the same way that a bicycle is irrelevant for crossing an ocean. Nuclear pulse propulsion offers more genuine promise. The concept, studied seriously under the name Project Orion in the late 1950s and early 1960s by physicists at General Atomics in San Diego, including Freeman Dyson, who joined the project in 1958 and became one of its most enthusiastic theoreticians. It involves detonating a series of small nuclear devices behind a spacecraft and riding the expanding plasma on a massive shock-absorbing pusher plate. The specific impulse achievable by this method, the measure of fuel efficiency in rocketry, would be orders of magnitude greater than chemical propulsion. Dyson's own analysis in the early 1960s suggested that an Orion-class spacecraft could reach perhaps 3% of light speed with a sufficiently large nuclear pulse system. At 3% of light speed, the journey to Proxima Centauri would take approximately 140 years. Still a long time by human standards. Still within the realm of multi-generational ships or suspended animation scenarios. Nuclear pulse propulsion involves detonating small nuclear explosives behind a spacecraft to generate thrust. Brutal and theoretically effective at accelerating heavy payloads, but requiring the launch of nuclear weapons into space, an approach banned under current international treaties. Project Orion was discontinued in 1965, a casualty of the Partial Nuclear Test Ban Treaty signed in 1963, which prohibited nuclear detonations in space. The physics, however, remained sound. The concept never died. It simply waited, as many ambitious ideas do, for a political environment that might tolerate it. Nuclear fusion propulsion would be cleaner and potentially faster. A fusion rocket, rather than detonating bombs externally, would ignite controlled fusion reactions within a chamber and direct the resulting plasma as exhaust. The theoretical exhaust velocities achievable with fusion, particularly with advanced catalyzed fusion schemes or the deuterium-helium-3 reactions proposed for the British Interplanetary Society's Daedalus study in the 1970s, could reach several percent of light speed. The Daedalus study, led by Alan Bond and a team of engineers and scientists, concluded in 1978 that a robotic probe could reach Barnard's star in approximately 50 years of travel, using a staged fusion rocket fueled by helium-3, mined from Jupiter's atmosphere. It was an extraordinary piece of engineering analysis, detailed, rigorous, honest about its assumptions. It was also entirely beyond any technology available then or now. The helium-3 mining alone requires infrastructure that does not exist. The ignition system for the fusion reactions requires precision that no fusion reactor on Earth has yet achieved. The shielding against the interstellar medium at those speeds requires materials that remain speculative. And then there is Breakthrough Starshot, the most recent, most publicly visible, and most technically creative attempt to define a credible path to another star. Announced on April 12, 2016, the Breakthrough Starshot initiative proposed to develop a fleet of light-sail interstellar probes capable of making the journey to the Alpha Centauri star system, 4.34 light-years away. The concept was elegant in its ambition. Abandon the idea of a large human-carrying vessel entirely. Instead, reduce the spacecraft to something the size of a postage stamp, a gram-scale chip carrying cameras, sensors, and a communications laser, and attach it to a light sail, a thin reflective membrane meters across but nanometers thick. Then accelerate this tiny package using a ground-based array of lasers, pushing it to 20% of light speed in a matter of minutes. At that speed, the journey to Proxima Centauri would take just over 20 years. The concept captured the imagination of physicists and engineers worldwide. A traditional rocket would carry the craft to space. Once it was some 37,000 miles from Earth, the lasers would light up, shooting 100 gigawatts of power at the light sails, whose combined photons would slam forward like wind on a sailboat. 10 minutes later, the spacecraft would be zooming at 20% of light speed, already halfway to Mars, on its way to hit Alpha Centauri in a couple of decades. And yet, by September 2025, the project was quietly placed on indefinite hold, its $100 million pledge reduced to a trickle of roughly $4.5 million actually spent. The engineering problems that the Starshot team had identified, and to their credit, they identified them honestly and early, turned out to be more resistant than the initial optimism had allowed. At Starshot's founding, the group identified around 30 problems to be solved, before anyone could send an interstellar probe anywhere. The light sail material needed to survive the laser pulse without vaporizing. The laser array required to achieve 100 gigawatts of coherent, focused power simply does not exist and would cost far more than $100 million to build. The communication system for a gram-scale craft to transmit images across 4 light-years of space remained what one engineer involved in the project called the elephant in the room. Substances that can withstand both the rigors of near-light speed and the shock of a laser blast tend to be heavy, and the vision required a sail 4 meters wide, weighing only a gram. Harry Atwater at the California Institute of Technology led the materials research, focusing on silicon nitride as a candidate for the sail substrate. His team found silicon nitride as the leading candidate. They published that result in 2022, demonstrating that engineers could fabricate it at submicron thicknesses, less than 1/10 the thickness of plastic wrap, and that ultra-thin wafers of the material could be assembled into a larger structure that is mostly reflective and does not absorb much light. The work was genuine progress, but it was one solution to one problem in a list of 30. Research continues. A 2025 study published in Nature Communications by a team using neural topology optimization found a novel pentagonal photonic crystal design that offered significant fabrication cost reductions for light sail reflectors, a meaningful incremental advance. The engineering frontier has not collapsed. It has simply revealed its true scale. The honest conclusion, standing at this point in the exploration, is that no propulsion system currently exists or is currently under active development that could send any payload, human or robotic, to a nearby star in less than several centuries of travel time. Some researchers argue that nuclear fusion propulsion, if the remaining engineering obstacles are cleared within the next few decades, could make a 50 to 100-year robotic mission plausible within this century. Others are more cautious, noting that could be feasible and will be built are separated by mountains of engineering, politics, and funding. Some researchers think the answer lies in photon propulsion, variations on the light sail concept, and that the Starshot pause is merely a temporary setback in a decades-long program. Others think the interstellar medium erosion problem alone, at high relativistic speeds, makes the light sail concept fundamentally limited until new materials are developed that do not yet exist even theoretically. What all of them agree on is this: the distance is real, the obstacles are real, and the universe has not granted us an easy path. Every proposal that sounds like a solution contains, somewhere inside it, an unresolved problem. Every confidence that the stars are within reach dissolves, on close inspection, into a list of requirements that has not yet been met. The journey, then, is not only across space, it is across the gap between aspiration and physics. And the first leg of the physical journey, the crossing of the interstellar medium itself, is not yet behind us. We are only at its edge, steering in, listening to the silence that is not quite silent, feeling the cold that has not yet reached its full depth. Step back, briefly, and take stock of where we are. We have left the heliosphere. We have described the interstellar medium, its composition, its structure, its hostility at speed. We have surveyed the full catalogue of propulsion concepts and found each one honest about its own limitations. Now the path continues outward, deeper into that medium, toward the first destination, the red dwarf Proxima Centauri, the closest star, and the world that orbits it in the zone where water could theoretically exist. That world is one of the strangest objects our telescopes have yet encountered. What we know about it, and what we cannot know, is the subject of what comes next. The distance remaining to Proxima Centauri from the heliopause is approximately 4.1 light-years. At the fastest speed a human artifact has ever traveled, this leg alone would take roughly 23,000 years. The cold in the interstellar medium between here and there averages somewhere below -200 degrees Celsius in the neutral regions. Though the hot ionized component of the local bubble runs paradoxically warmer, its temperature measured in millions of degrees, and its density measured in fractions of a single atom per cubic centimeter. You would feel nothing from that heat. The density is too low. You would feel only the vacuum, the radiation, and the dark. Proxima Centauri is burning ahead, somewhere in the southern hemisphere's constellation of Centaurus, invisible to the naked eye, too faint, too red, too dim. It has been burning for approximately 4.85 billion years, and it will continue burning for another 4 trillion years or so, longer than the current age of the universe by a factor of nearly 300. It is, in cosmic terms, barely getting started. What waits there is not what you might hope. Approaching Proxima Centauri across the interstellar dark, the first thing you notice is that the star refuses to look like a star. From a distance of several light months, it appears in your instruments as a faint reddish point, dimmer than a dozen background stars visible in the same field of view, barely distinguishable by brightness alone. You would have to know precisely where to look. Proxima Centauri has a luminosity of approximately 0.00155 times that of our Sun, roughly 1/600th as bright. If you replaced our Sun with Proxima Centauri at exactly the same distance, the noonday sky on Earth would not be flooded with light. It would be something more like deep twilight. The surface of Earth would freeze. The oceans would begin their long conversion to ice. And yet, this dim, faint, nearly invisible object is not a failed or dying star. It is a star in the full prime of its life, burning steadily on the main sequence, fusing hydrogen to helium in its core with an efficiency and longevity that our Sun cannot match. Proxima Centauri is what astronomers classify as an M-type dwarf, a red dwarf, and it belongs to the most numerous class of star in the galaxy. Approximately 70% of all stars are M-type dwarfs. The galaxy is built from dim red fires. Our own Sun, a G-type yellow dwarf, is a relative rarity. Proxima Centauri has a mass of about 0.12 times the Sun's mass, and a radius approximately 14% of the Sun's radius. It is so small that if our Sun were the size of a typical front door, Proxima Centauri would be the size of a large grapefruit. Its core burns cooler and slower, which is precisely why it will outlast our Sun so dramatically. Stars exhaust themselves in proportion to their luminosity. The brighter the burn, the faster the fuel disappears. Our Sun, roughly 4.6 billion years into its life, has perhaps another 5 billion years before it begins to exhaust its core hydrogen and swell into a red giant. Proxima Centauri, at its current burn rate, will continue fusing hydrogen for an estimated 4 trillion years. The universe itself is only about 13.8 billion years old. Proxima Centauri has barely touched its fuel reserves. This longevity sounds reassuring. It sounds like stability, like patience, like a steady and reliable light. But here is where the comfortable picture begins to dissolve. Proxima Centauri is a flare star, one of the most violently active examples of its class. Its surface, despite being cooler than the Sun's, is magnetically volatile in ways that bear little resemblance to solar behavior. The star's deep convective zone drives a turbulent magnetic dynamo, producing surface magnetic fields far stronger relative to its size than anything the Sun generates. These fields generate star spots, active regions, and, most significantly for anything in the vicinity, enormous stellar flares. Not gentle flares like the ones our Sun occasionally produces, events that cause radio blackouts on Earth and require us to reroute satellites. Proxima's flares are episodes of catastrophic violence. They release enormous bursts of ultraviolet radiation and X-rays, energetic particle streams, and coronal mass ejections, clouds of magnetized plasma hurled outward from the stellar surface at millions of kilometers per hour. In 2019, a team of researchers led by astronomer Park Lloyd of the University of Arizona, as part of the Iriscope Fast Transient Engine collaboration, detected a superflare from Proxima Centauri that briefly increased the star's ultraviolet output by a factor of roughly 14,000. This was not an exceptional event in Proxima's history. It was simply one the instruments happened to catch with sufficient detail to characterize. Studies of Proxima's flare frequency suggest the star produces significant flares roughly every few days, and superflares at somewhat longer intervals. Throughout its multi-trillion-year lifetime, Proxima Centauri has been doing this continuously, blasting its surroundings, flooding the nearby volume of space with radiation, scouring everything within range. Feel what this means if you are aboard a vessel approaching Proxima Centauri. You are crossing the interstellar medium, deep in transit, and then the instruments alert you to a sudden surge in ultraviolet flux. The source is ahead. The star has released a flare. The UV levels spike within minutes. Your shielding absorbs what it can. The electronics register the pulse. If you are close enough, within the orbital radius of any potential planet, the radiation dose on an unshielded human body would arrive at levels hundreds of times beyond what would cause acute radiation sickness. The flare might last minutes. The next one might follow in days. Proxima Centauri does not burn quietly. It announces itself. It tears at the space around it with electromagnetic violence that no planet in its vicinity can simply ignore. A pause here, a genuine dwelling on this point, because it matters profoundly for what comes next. The flare environment around Proxima Centauri is not a peripheral consideration to be mentioned and set aside. It is the central physical reality that shapes everything about the system. It shapes whether the planet we are about to examine has an atmosphere. It shapes whether any probe we send there will function after arrival. It shapes whether life, if it ever arose in this system, could have survived long enough to become complex. Proxima burns long and dim, yes, but it burns explosively. It is a small star with a violent temper, and its neighborhood bears the marks. Now turn attention to what orbits it. The planet is there, small, rocky, approximately Earth mass, circling in the zone where liquid water could theoretically exist. It was found in 2016. And the story of its finding, and of everything we have learned about it since, is one of the more emotionally complicated chapters in the history of exoplanet science. The announcement came on August 24, 2016, from the European Southern Observatory. Astronomer Guillaume Anglada-Escudé, then at Queen Mary University of London, and his colleagues published their detection of Proxima Centauri b in the journal Nature. They had used the radial velocity method, measuring the tiny Doppler shift in Proxima's light caused by the gravitational tug of an orbiting planet, to establish the presence of a body with a minimum mass of roughly 1.06 times Earth's mass, orbiting Proxima Centauri at a distance of about 0.0485 astronomical units, completing one orbit every 11.2 Earth days. The news moved through the scientific community and the broader public with unusual speed. Here was a planet, an approximately Earth-sized planet, orbiting within the habitable zone of our nearest stellar neighbor. The nearest, potentially habitable world was not hundreds of light years away, scattered among the distant stars of Kepler's survey fields. It was next door, cosmically speaking. It was at the first address past our own. The reaction was, understandably, one of profound excitement. The possibility of liquid water, the possibility of an atmosphere, the possibility, whispered rather than stated, of life. For a moment, the universe seemed to have arranged itself generously. Then the details arrived, and the excitement became more complicated. Proxima Centauri b orbits its star at a distance approximately 20 times closer than Earth orbits the Sun. This extreme proximity is necessary because Proxima is so faint. To sit in the habitable zone, where temperatures could permit liquid water, the planet must be very close indeed. But that closeness carries profound consequences. The most immediate is tidal locking. At 0.0485 astronomical units from a star the size of Proxima, gravitational tidal forces are strong enough that over geological timescales, they would likely synchronize the planet's rotation with its orbital period. Though, depending on orbital eccentricity, a spin-orbit resonance similar to Mercury's might also be possible. One side of the planet would face the star permanently, bathed in continuous, if dim, light. The other side would face eternal night. The day side might maintain temperatures above freezing. The night side might be cold enough to freeze any atmosphere solid, a process called atmospheric collapse, in which gases condense into ice on the permanent night hemisphere, and the planet loses its atmosphere from the outside in. Some climate models suggest that if Proxima b has a sufficiently thick atmosphere, heat transport by atmospheric circulation could moderate the temperature difference between day and night sides, preventing collapse. Computer models published by climate scientists at the Paris Institute of Pierre-Simon Laplace, including work by Jeremy Leconte and colleagues in 2015, had examined this problem for tidally locked planets generally and found that certain atmospheric configurations, particularly those with abundant carbon dioxide or nitrogen, could sustain reasonable surface temperatures even in the permanent night region. If Proxima b is lucky with its atmospheric composition and mass, tidal locking might not be a death sentence. But Proxima b's atmosphere faces a far more fundamental problem than tidal locking. It must exist first. And the evidence suggests that existence is not guaranteed. In 2017, NASA space scientist Catherine Garcia Sage at the Goddard Space Flight Center published a study in the astrophysical journal Letters that modeled what would happen to an Earth-like atmosphere if it were placed on a planet at Proxima b's orbit. The model used Earth's own atmosphere, magnetic field strength, and gravity as proxies for Proxima b, then applied the radiation environment provided by observations of Proxima Centauri's ultraviolet and X-ray output. What Garcia Sage and her colleagues found was not ambiguous. Proxima's radiation strips atmospheric material away at rates up to 10,000 times faster than the solar wind strips Earth's atmosphere. Even with a magnetic field comparable to Earth's, the planet's upper atmosphere would be continuously ionized and heated, driving a polar wind of escaping ions that would drain an Earth-equivalent atmosphere within geological timescales, perhaps as little as a few 100 million years. Atmospheric loss rates are so high that habitability is implausible, said Jeremy Drake, an astrophysicist at the Harvard-Smithsonian Center for Astrophysics and co-author of that study. Those words deserve to be held for a moment. Not merely challenging, not uncertain, implausible. Some researchers think the picture is genuinely that bleak. Others push back, noting that the model assumes Earth-like starting conditions and does not account for scenarios in which Proxima b formed with a much larger initial volatile inventory, perhaps as an ocean world with many times Earth's water budget, or in which the planet's internal geology provided continuous atmospheric replenishment through volcanism. Astronomer Victoria Meadows of the University of Washington, leading a comprehensive habitability study published in Astrobiology in 2018, modeled several dozen distinct evolutionary scenarios for Proxima b's atmosphere, ranging from a completely desiccated oxygen world to an Earth analog, and found that some scenarios are habitable while others are not, but that distinguishing between them from Earth's telescopes remains extraordinarily difficult. The honest scientific position, as of today, is that we do not know whether Proxima b has an atmosphere, and if it does, we do not know whether it is the kind of atmosphere that supports liquid water on a surface. What we can say is that the environment is hostile in ways that make optimism difficult to sustain without specific supporting evidence. There is also the matter of whether the planet is the kind of planet we imagine. Proxima b is detected through radial velocity measurements, which yield a minimum mass. The actual mass could be higher, depending on the inclination of the orbit relative to our line of sight. If the orbit is highly inclined, Proxima b could be a significantly more massive body than the estimates suggest. The planet's radius, composition, and surface character remain unobserved. It has not been directly imaged. We have not detected its atmosphere spectroscopically. We know it is there. We know roughly how massive it is. We know its orbital period. Everything else is inference and model. And yet, this uncertain, battered, possibly atmosphereless rock, orbiting a violently flaring red dwarf, is the closest potentially habitable planet in the universe to our own, if life exists anywhere outside our solar system, within reach of our current technology. Proxima b is the leading candidate address. That is, in its way, a summary of how generous the universe has been with us, or at least with proximity. There is something else worth noting. Proxima Centauri is not alone. It is gravitationally associated, loosely at enormous separation, with the Alpha Centauri system, a pair of sun-like stars orbiting each other at an average distance of roughly 23 astronomical units, roughly the orbital distance of Uranus from our Sun. Alpha Centauri A, the brighter of the two, is a G-type star slightly larger and more luminous than our own Sun. Alpha Centauri B is a K-type star, slightly smaller and cooler. They orbit their common center of mass with a period of about 79.9 years. Proxima Centauri orbits this binary pair at a distance of approximately 0.22 light-years, about 13,000 astronomical units, taking perhaps 1,000,000 years or more to complete a single orbit around the binary, if it is indeed gravitationally bound and not simply passing nearby on a coincidentally similar trajectory. The gravitational relationship between Proxima and the Alpha Centauri binary is itself a matter of some ongoing scientific discussion. Some researchers have argued that Proxima is genuinely bound to the Alpha Centauri system, sharing a common proper motion through the galaxy that would be difficult to explain by chance alone. Others have pointed out that the binding energy is small enough that the relationship may be genuinely uncertain over very long timescales. For our purposes, the practical consequence is clear. When we travel to the Alpha Centauri system, Proxima Centauri is part of it. They are a triad, 2 bright twins and 1 dim, violent companion. The approach to Alpha Centauri A and B is a different experience than the approach to Proxima. When Proxima refused to announce itself, the Alpha Centauri pair blazed. From a distance of several light months, Alpha Centauri A and B are the two brightest objects in the sky beyond the interstellar dark, outshining anything except each other. They orbit close enough that their light appears merged from Earth, making them the third brightest star system in Earth's night sky, a single brilliant point in the constellation Centaurus, known since antiquity. Up close, they resolve into two distinct suns. One, pale yellow, slightly warmer than our own. The other, slightly more orange, slightly cooler. Stand for a moment on a hypothetical observation point between the two stars, equidistant from both. Alpha Centauri A, with a surface temperature of approximately 5,790 Kelvin, nearly identical to our Sun's 5,778 Kelvin. Burns with a familiar, comforting color. Its light feels, at some instinctual level, like sunlight. Alpha Centauri B, at approximately 5,260 Kelvin, casts a slightly warmer-toned light, more golden than white. The two together create a doubled illumination. Shadows fall in two directions, at angles that shift as the stars orbit each other. The binary orbit has a period of approximately 79.9 years, so at any given moment, the angular separation between the two stars depends on where in the orbit you observe them. At closest approach, they are only 11 astronomical units apart, roughly the orbital distance of Saturn from our Sun. At farthest separation, they reach more than 35 astronomical units. The question of whether this binary system contains planets has been one of the more frustrating puzzles in nearby stellar astronomy. In 2012, Xavier Dumasque and colleagues announced the detection of a roughly Earth-mass planet orbiting Alpha Centauri B, a planet with an orbital period of just 3.24 days, far too close to the star for habitability, but exciting as a proof of concept for Earth-mass planets in this system. The announcement was subsequently disputed. Other research teams, reanalyzing the radial velocity data with different statistical approaches, concluded that the signal was likely an artifact, a ghost produced by the data reduction process, rather than a real planetary body. The controversy was not fully resolved. In 2021, a team led by Kevin Wagner at the University of Arizona reported a candidate planet around Alpha Centauri A, detected via direct mid-infrared imaging. But this detection also remains unconfirmed and contested. Some researchers think it may be a background object or an instrumental artifact. Others regard it as a genuine, tantalizing signal. What the binary environment does do, unambiguously, is complicate the formation of planets in certain orbital configurations. Two stars orbiting each other gravitationally stir the protoplanetary disk during the planet-forming epoch, disrupting the orbital stability of material at certain distances. Planets can form in very close orbits to one component of the binary, so-called S-type or circumstellar orbits, or in very wide orbits encompassing both stars, so-called P-type or circumbinary orbits. But intermediate distances, the region where temperate habitable zone planets would naturally form around a single star, can be gravitationally agitated to the point of instability. For Alpha Centauri, computer simulations suggest that stable orbits exist in the habitable zones of both stars, despite the mutual perturbations, but that the formation of planets in those zones may have been partially disrupted by the binary interaction early in the system's history. Whether those zones contain planets today remains genuinely unknown. The fact that we cannot answer this question, whether our two nearest Sun-like stellar neighbors have Earth-like planets in their habitable zones, is itself a statement about the limits of current observation. Alpha Centauri A and B are, from the perspective of Earth-based astronomy, practically on our doorstep. They are the closest stars we can clearly see with the naked eye from the southern hemisphere. And yet, their planetary systems remain almost entirely opaque to us. We can build telescopes sensitive enough to detect the wobble caused by a planet 100 light-years away. But the nearby binary system confounds our methods. The stellar signal from the companion star bleeds into the data and obscures the planetary signal we are searching for. We are trying to read a faint pencil mark on a page that someone is simultaneously shaking. Something here deserves attention. The Alpha Centauri system is close enough that a laser communication signal from any probe we send there would take only 4.37 years to return. A robotic explorer at Alpha Centauri could, in theory, return detailed images and spectroscopic analysis within a human lifetime from the moment it arrives. This proximity, 4 years for light to return home, gives the Alpha Centauri system a unique status in interstellar exploration. It is the only stellar system where the round-trip light travel time falls within the span of a human career. Everything beyond it recedes into timescales that strain the meaning of the word conversation. A message to Barnard's star takes 6 years one way, to Sirius nearly 9. The universe does not make communication easy across stellar distances, but it makes it least impossible here at the nearest addresses. This is worth pausing on as we prepare to move deeper into our journey. The Alpha Centauri system, Proxima included, represents not just our nearest neighbors, but the boundary of any plausible near-term interstellar engagement. It is where the first probes, if they are ever built and launched, would go. It is where the first signal, if one is ever received from another technological civilization in our cosmic vicinity, would most plausibly originate. It is the edge of the most intimate version of interstellar reach. Beyond Alpha Centauri, the distances only grow. The next stars in the catalogue: Barnard's star at 5.96 light-years, Wolf 359 at 7.86 light-years, Sirius at 8.6 light-years, are not appreciably farther in absolute terms, but they are separated from us by gaps that grow with each entry in the table. Each additional light-year is another 9.46 trillion kilometers of interstellar medium to cross, another decade of travel time added to the fastest conceivable probe, another several years added to the round-trip communication delay. The journey continues outward. The warmth of the Alpha Centauri suns fades behind. Ahead, the interstellar medium opens again into its familiar silence. Barnard's star, tiny, ancient, moving faster across the sky than any other known star, burns somewhere in the constellation Ophiuchus, a destination we will approach before turning finally toward the blue brilliance of Sirius. But first, a re-entry point for those who have drifted. We are approximately 4.4 light-years from Earth. We have passed through the heliosphere, crossed the interstellar medium, examined Proxima Centauri and its battered, uncertain planet, and looked closely at the Alpha Centauri binary, our most celebrated stellar neighbors, whose planetary systems remain tantalizing and largely invisible to our instruments. Now the journey pushes on into a darker, stranger territory, where the stars themselves become more peculiar, and where the implications of the crossing accumulate toward questions that touch not just engineering or biology, but something deeper. The next star is older than most things we will encounter. It is smaller than Proxima. It carries, embedded in its ancient motion, a hint of something long debated, a possible planet found and found again. And the story of its discovery is inseparable from the story of a man who spent decades watching a single point of light move imperceptibly across the sky, and who found in that motion something that had never been seen before. Barnard's star is named for the man who found it. Edward Emerson Barnard, working at Yerkes Observatory in Wisconsin in 1916, compared photographic plates taken decades apart and discovered that one apparently ordinary faint red star in Ophiuchus was moving across the sky at a rate nearly 10 times faster than any previously known star, 10.4 arc-seconds per year relative to the background stars, a rate so high it became the defining measure of what astronomers call proper motion, the apparent angular movement of a star across the celestial sphere due to its actual velocity through space. Barnard's star moves so quickly across our sky, relative to the background stars, because it is moving through the galaxy at roughly 140 kilometers per second relative to our Sun, and because it is very close, 5.96 light-years, the fourth nearest stellar system and the nearest single star to our Sun, after the triple Alpha Centauri system. It is a red dwarf, like Proxima, smaller, cooler, with a mass about 0.144 times the Sun's. It is also ancient. Estimates of Barnard's star's age run between 7 and 12 billion years, making it one of the oldest stars in the solar neighborhood. It has been burning its dim red light since the universe was young, since the Milky Way was still assembling itself from merging protogalactic fragments, since the chemical elements heavier than helium were still being forged in the first generations of massive stars. It predates our solar system by several billion years. It has watched the sky change, the nearby stellar neighborhood reshuffling itself through proper motions across timescales that dwarf the entire span of complex life on Earth. Does Barnard's star have planets? The question has a complicated history. In 1963, astronomer Peter van der Kamp, who had spent years making extraordinarily careful measurements of Barnard's star's proper motion at the Sproul Observatory in Swarthmore, Pennsylvania, announced that the star showed a slight sinusoidal wobble in its path across the sky, the kind of wobble expected if an unseen companion planet were gravitationally pulling on the star as both moved through space. Van der Kamp refined his analysis over subsequent years, and by the early 1970s was arguing for the existence of two companion planets, each several times the mass of Jupiter. He devoted much of his career to this finding, and for years it was taken seriously. Then, in the mid-1970s, other astronomers began examining the Sproul data more critically. George Gatewood at Allegheny Observatory and Heinrich Eichhorn at the University of Florida found that the apparent wobbles in Barnard's star's motion correlated suspiciously with adjustments and changes made to the Sproul refractor telescope itself, lens replacements, modifications to the instrument. The wobbles were not in the star, they were in the measuring device. Van der Kamp's planets dissolved back into the data noise. He never accepted this conclusion, continuing to argue for his finding until his death in 1995. The scientific community had moved on. In 2018, a new detection was announced. A team led by Ignasi Ribas of the Institute of Space Sciences in Barcelona, using data from 7 different telescopes compiled over 16 years of radial velocity measurements, reported evidence for a planet with a minimum mass of about 3.2 times Earth's mass, a so-called super-Earth, orbiting Barnard's star at a distance of about 0.4 astronomical units, far outside the habitable zone for this faint star, with an orbital period of 233 days. The signal was described as tentative but intriguing. Subsequent analyses have cast doubt on its planetary origin, with some researchers suggesting the signal may be produced by stellar activity on the star's surface rather than by a planetary body. As of the most recent assessments, Barnard's star's planetary status remains genuinely unresolved. Perhaps a candidate, an open question. What is not in doubt is the star's character. It is old, it is small, it is metal poor, meaning it formed from gas that had not yet been enriched by many generations of stellar nucleosynthesis, a composition that may make it less favorable for rocky planet formation than younger, more metal-rich stars. It rotates extremely slowly, completing one rotation every 130 days or so, a consequence of its great age and the gradual loss of rotational energy over billions of years. Older red dwarfs like Barnard's star tend to be less flare-active than young ones like Proxima, whose magnetic activity is still fueled by relatively rapid rotation. In this regard, Barnard's star is quieter than Proxima. Its radiation environment, while still harsh by the standards of any solar system planet, is somewhat less violent. From the perspective of a traveler at Barnard's star, the sun shines behind you at a distance of 5.96 light-years, a bright bluish-white point considerably dimmer than from Earth, but still the brightest star in that sky. Alpha Centauri appears as a bright double point, still among the more prominent stars. Proxima Centauri is invisible without instruments. The sky at Barnard's star is, in most respects, a slightly rearranged version of Earth's night sky. The same constellations, shifted and skewed by the changed vantage point. The familiar patterns slightly distorted, as some stars are nearer and some farther than their apparent Earth-sky positions suggest. The time required to reach Barnard's star from Earth, at our fastest achieved speed, is approximately 105,000 years. From Alpha Centauri, it is an additional journey of nearly 2 light-years. The interstellar medium between is similar to what we have already crossed. Thin, cold, radiation-threaded, indifferent. The pattern is becoming clear. Each star reveals a new set of unknowns. Each potentially habitable world turns out to be threatened, uncertain, or simply opaque. The distances compound. The obstacles multiply. The universe does not simplify as you move through it. It deepens. The stellar neighborhood does not improve as it expands. Moving outward from Barnard's star, the catalogue of nearby stars reveals a pattern that is, depending on your temperament, either humbling or clarifying. The vast majority of the stars within 10 light-years of Earth are faint, cool, dim red dwarfs, objects so intrinsically feeble that none of them are visible to the naked eye from Earth, despite being among the closest stars in the galaxy. Of the roughly 50 stellar systems within 13 light-years of the Sun, more than 40 are red dwarfs. The galaxy is not a place of abundant sun-like stars, separated by moderate distances. It is a place of dim red fires, widely spaced, each burning for trillions of years in near total obscurity, and between them, mostly nothing. Wolf 359 makes this pattern concrete. Located 7.86 light-years from Earth, in the constellation Leo, it is one of the faintest stars known, with a luminosity of approximately 0.1% of the Sun's, so dim that even at its relatively close distance, it would require a telescope of some power to see from Earth. It has a mass of approximately 11% of the Sun's, barely above the minimum threshold for hydrogen fusion. Stars below about 8% of solar mass cannot sustain nuclear burning at their cores and become brown dwarfs instead, objects too massive to be planets, but too faint to be stars. Wolf 359 sits just above that line. It is, in the most literal astronomical sense, barely a star. It has a surface temperature of roughly 2,800 Kelvin. By comparison, the Sun burns at about 5,778 Kelvin. The surface of a wood fire burns at roughly 1000 Kelvin. Wolf 359 is not much more than twice as hot as an open flame. Its light is so far toward the infrared end of the spectrum that a human eye, standing on any planet in its vicinity, would see it not as white or yellow, but as deep, saturated orange-red, the color of an ember, the color of the very last glow of something that has almost stopped burning. Except that it has not almost stopped. It is barely getting started. It will burn this dim, this cool, this ancient-seeming for trillions of years more. Wolf 359 is a flare star like Proxima. Most young M-type dwarfs are. It flares erratically, releasing bursts of ultraviolet and X-ray radiation in events that briefly outshine its ordinary luminosity by factors of dozens. Any planet orbiting within its habitable zone, which, because the star is so faint, would have to orbit within a few tens of thousands of kilometers, would face the same brutal radiation environment we discussed at Proxima Centauri, possibly worse given the star's active phase. No confirmed planets have been detected around Wolf 359. The system's poverty of light extends to its planetary census. Approaching Wolf 359 in imagination, the most striking sensation is one of diminishment. The Sun, now 7.86 light-years behind you, has become merely a bright star. Prominent, certainly, among the brightest in your sky, but a point. The star ahead is a reddish glow, barely distinguishable from a background red giant, if you do not know exactly where to look. The interstellar medium around you is the same thin, cold medium you have been crossing for the entire journey, slightly varying in density as you pass through different phases of the local bubble's interior, but fundamentally the same vast, austere, radiation-threaded near vacuum. The catalogue continues its recitation. Ross 154 at 9.69 light-years, a red dwarf. Ross 248 at 10.3 light-years, a red dwarf. Epsilon Eridani at 10.5 light-years is one of the few nearby stars with a spectral type similar to the Sun's, a young K-type dwarf with a known debris disk, and possibly one large planet detected through radial velocity measurements. Tau Ceti at 11.9 light-years, another K-type star with a complex and controversial planetary system, including several candidate planets of various masses. These are the exceptions. Between them, the galaxy is filled with M-type dwarfs that human culture has barely named, stars that appear in catalogues by number, that generations of observers passed over in their searches for sun-like companions. The implications of this stellar demography are worth sitting with for a moment. If red dwarf stars are the dominant stellar population of the galaxy, if they outnumber all other star types combined by enormous margins, then when we ask where life might exist in the universe, we are really asking whether life can survive and thrive around red dwarfs. The Proxima Centauri and Wolf 359 problem is not a local curiosity. It is a galaxy-scale question. 70% of all stars are potential flare stars with tight habitable zones and violent magnetic activity cycles. If life cannot gain a foothold around red dwarfs, the galaxy is a lonelier place than the raw star count suggests. Some researchers are optimistic, arguing that life, if it arose early enough on a red dwarf planet, might develop robust adaptations to radiation, or that certain geological configurations might shield surface life from stellar flares. Others remain deeply skeptical that the right conditions can be maintained long enough for complex life to emerge. We do not have an answer. What we have, instead, is Sirius. The approach to Sirius is unlike anything that has come before on this journey. From a distance of several light months, Sirius A blazes with a brilliance that makes everything else in the sky irrelevant. It is the brightest star in Earth's night sky for a reason. Not because it is especially close, though at 8.6 light-years it is indeed relatively nearby, but because it is intrinsically luminous. Sirius A has a surface temperature of approximately 9,940 Kelvin, nearly twice the temperature of our Sun, and a luminosity roughly 25 times greater. It radiates predominantly in blue-white light, the kind of cold, hard, high-energy illumination that looks nothing like sunshine. It looks like the light of a welding arc, clean and merciless and blue. Sirius A is classified as an A-type main sequence star. Type A stars are among the most beautiful in the sky. Hot, bright, blue-white, dramatic. They are also, by the standards of cosmic longevity, transient. Our Sun will last about 10 billion years on the main sequence. Sirius A, burning so much brighter and hotter, will exhaust its core hydrogen in roughly 1 billion years, less than 1/10 the Sun's lifespan. By the time our Sun moves off the main sequence and begins its expansion into a red giant, Sirius A will have already finished its life, collapsed, shed its outer layers in a planetary nebula, and compressed into a white dwarf. The brilliant blue-white star will be gone. And this is precisely what happened to Sirius B. Sirius B is a white dwarf, the compressed remnant of what was once a star considerably more massive than Sirius A. At some point in the relatively recent astronomical past, perhaps 120 million years ago, the star that became Sirius B was probably a blue-white giant, perhaps 5 times the mass of our Sun, burning with extraordinary profligacy through its nuclear fuel. It outshone Sirius A dramatically. It likely completed its entire main sequence lifetime in only a few tens of millions of years. Then, it swelled into a red giant, shed its outer layers in a planetary nebula event, and left behind its exposed core, a sphere roughly the size of Earth, but containing a mass roughly equal to the Sun's. Sirius B is a teaspoon of material that would weigh several tons on Earth. It is a stellar corpse, cooling slowly across millions of years, its surface still hot, around 25,000 Kelvin, but no longer powered by fusion, merely radiating away the stored heat of its violent past. The existence of Sirius B was deduced before it was ever seen. Friedrich Wilhelm Bessel, the same man who made the first stellar parallax measurement of 61 Cygni in 1838, noticed in 1844 that Sirius A showed a slight irregular wobble in its proper motion across the sky, as if being gravitationally tugged by an unseen companion. Bessel predicted the companion's existence and approximate mass years before anyone could detect it. His prediction was confirmed in 1862, when the American optician Alvan Graham Clark, testing a new refracting telescope, accidentally pointed it at Sirius and saw the tiny, faint point of light orbiting close to the brilliant primary. Sirius B, later nicknamed the pup to Sirius A's dog star, was the first white dwarf ever discovered. Its existence, once physicists understood what it was, raised profound questions about the ultimate fate of all stars, including our own Sun. Sirius has been known to human beings for as long as human beings have recorded astronomical observations. The ancient Egyptians called it Sopdet, and its heliacal rising, the first morning in the year when Sirius reappears in the pre-dawn sky after its period of solar conjunction, marked the beginning of the Egyptian calendar year and coincided in the era of the Great Pyramids with the annual flooding of the Nile. The flood brought the fertile silt that sustained Egyptian civilization. Sirius, rising with the sun in late July, announced that the waters were coming. A star 8.6 light-years away was woven into the agricultural cycle of a Bronze Age civilization. The light now reaching Earth from Sirius left the star 8.6 years ago, while you were alive during events you remember. It has been crossing this particular stretch of interstellar medium since before most of the people watching this were born this year. From the surface of any hypothetical planet orbiting Sirius A, the experience of that starlight would be extraordinary and unforgiving. At an equivalent habitable zone distance, where temperatures might permit liquid water, the radiation received from Sirius A would be intense in wavelengths that damage biological molecules, the ultraviolet flux far higher than anything Earth's surface life experiences. Life, if it were to exist in the Sirius system, would need substantial UV shielding, either from ozone chemistry in a thick atmosphere or from some equivalent biological adaptation. Sirius B adds a further complication. Its intense radiation during its planetary nebula phase, roughly 120 million years ago, would have irradiated the entire system with enough energy to strip or chemically alter the atmospheres of any planets in close orbit. Whether any planets exist in the Sirius system is unknown. No confirmed detections have been made, and the system's youth, relative stellar activity, and binary dynamics make planet hunting here particularly difficult. Pause here and take stock of the journey so far. We have traveled from the heliosphere outward across 8.6 light-years of space, visiting 6 stellar systems: Proxima Centauri, Alpha Centauri A and B, Barnard's Star, Wolf 359, and now Sirius. At every stop, we have found either red dwarfs with violent radiation environments and uncertain planets, or a binary system whose planet formation history remains opaque, or a brilliant hot star with a stellar corpse companion and no confirmed worlds. Not a single planet in this entire volume of space has been confirmed to have the atmosphere, temperature, and stability required for life, as we understand it. Not one. This is not pessimism. It is the current state of the observations. The survey is incomplete. The instruments are limited. Some researchers argue that this incompleteness is the main story, that habitable planets are almost certainly present in these systems, waiting to be found by telescopes not yet built. Others find the silence of the nearby stellar catalogue genuinely significant, a data point in its own right. The nearest stars are not, as far as we can tell, teeming with comfortable blue-green worlds. They are, as far as we can tell, largely hostile. Beautiful, complex, ancient, but hostile. And throughout all of this discussion of stellar physics and planetary atmospheres, one question has been waiting with patient insistence. The large loop, planted at the beginning, has not yet been resolved. What would the journey do to a human body? The human body is, from a physiological standpoint, a system optimized for a very specific set of conditions. It evolved on the surface of a single planet, under a specific gravitational acceleration, shielded by a specific magnetic field and atmospheric column from the radiation of a specific middle-aged star. Remove any one of those conditions, and the body begins to fail. Remove all of them simultaneously, and the failure is comprehensive, systematic, and accelerating. The best data we have on extended spaceflight comes from the International Space Station, orbiting Earth at an altitude of approximately 400 kilometers, still well within Earth's magnetic field, and thus still partially shielded from galactic cosmic radiation. Even there, even with that protection, even with vigorous daily exercise protocols, even with carefully managed nutrition and sleep schedules, the human body deteriorates. Bone mineral density decreases at approximately 1 to 2% per month in microgravity. Muscle mass declines. The cardiovascular system, no longer working against gravity to pump blood upward to the brain, restructures itself in ways that cause problems on return to Earth. The eyes change, a condition called visual impairment and intracranial pressure syndrome, identified and studied extensively by NASA after several ISS crew members reported vision changes during long-duration missions, appears to be related to fluid shifts in the body, causing pressure changes around the optic nerve. The immune system is altered. The gut microbiome shifts. Sleep quality degrades. Scott Kelly's year-long mission aboard the ISS completed in March 2016, along with his identical twin brother, Mark Kelly, who remained on Earth, provided one of the most comprehensive datasets on long-duration spaceflight physiology. NASA geneticist Christopher Mason at Weill Cornell Medicine led the twin study analysis, published in Science in 2019, and found significant changes in gene expression, telomere length, cognitive performance, and microbiome composition in Scott Kelly relative to his Earthbound twin. Most changes reversed after Scott returned to Earth. Some did not. The telomere changes were particularly unexpected, and while not dangerous in themselves, they indicated a level of genomic instability that a longer mission would presumably amplify. These changes occurred on the ISS, inside Earth's magnetic field, on a 6-month to 1-year timescale. Now consider crossing the interstellar medium in a vessel beyond the heliosphere. Beyond the heliopause, the partial shielding from galactic cosmic rays provided by the solar wind's magnetic field is gone. Galactic cosmic rays are not like the relatively low-energy charged particles produced by the Sun. They are high-energy atomic nuclei, protons, alpha particles, ion nuclei, accelerated to relativistic velocities by supernova remnants, pulsars, and other violent astrophysical processes scattered across the galaxy. They arrive from all directions, with no preferred angle, with no way to simply face a shield toward them. They penetrate all practical thicknesses of conventional shielding, and worse, heavy shielding materials like lead or thick metal walls actually create secondary particle cascades when struck by the highest energy cosmic rays, sometimes producing more total radiation dose than the primary particle would have delivered through thin walls. Adding mass to the walls of a spacecraft beyond a certain point actively makes the radiation environment inside worse. This is not a problem engineering has solved. It is not a problem that appears close to being solved. Some researchers have proposed using water walls as shielding, large volumes of water surrounding habitable compartments, which absorb radiation more benignly than metals. Others have proposed magnetic shielding, large electromagnets generating fields around the spacecraft that would deflect some charged particles. These concepts reduce the dose, but do not eliminate it. A crew crossing to Proxima Centauri at the fastest plausible near-term spacecraft speeds, perhaps 1% of light speed, achievable in theory with advanced nuclear propulsion, would be in transit for approximately 420 years. 4 centuries of continuous galactic cosmic ray exposure at levels several times higher than the worst experienced on the ISS, with no possibility of evacuation to Earth, no possibility of medical intervention more sophisticated than whatever is aboard the vessel. The accumulated radiation dose would almost certainly be lethal many times over. The bone loss problem compounds with time. 4 centuries of even mild microgravity effects, assuming the ship cannot rotate to produce artificial gravity, which raises its own engineering challenges, would leave skeletal systems structurally compromised in ways that cannot be fully reversed by exercise alone. The cardiovascular restructuring would proceed until the bodies aboard are optimized for a low-gravity environment and would function poorly in any other. The psychological toll is less precisely quantifiable, but no less real. In 2010, the Mars 500 simulation conducted in Moscow, a 520-day isolation experiment in which 6 crew members lived in a sealed habitat without external contact, simulating a Mars mission, revealed that sleep disruption, sedentarism, psychological withdrawal, and subtle cognitive impairment accumulated over the course of the isolation period, even with crew selection for psychological resilience, even with structured schedules and communication with the outside world. A genuine interstellar crossing would offer no communication with the outside world at any timescale shorter than years. Mission control could not respond to an emergency in real time. The crew would be genuinely, definitively alone. More alone than any human beings in history, in an environment that offered nothing familiar, orbiting no star, crossing a void measured in light years. And there is the multi-generational problem. If the crossing takes centuries or millennia, even the most optimistic near-term propulsion scenarios involve decades, a single crew does not complete the journey. Generations do. The people who step off the vessel at Proxima Centauri are not the people who stepped on at Earth. They are the descendants of the founders, raised entirely in the artificial environment of the ship, shaped by its culture, its constraints, its physics. They would have been born in transit, educated in transit, partnered and reproduced in transit. Their entire experiential universe would be the ship. Their psychology, their physiology, their understanding of concepts like outside and horizon and weather would be alien to their ancestors. Whether they could function effectively upon arrival, in whatever environment awaited them, is genuinely uncertain. Geneticist Cameron Smith at Portland State University, examining the problem in 2014, suggested a minimum founding population of around 150 to 180 individuals to maintain adequate genetic diversity over a year multi-generational voyage, accounting for the bottlenecks and drift that would accumulate over centuries. More recent modeling by Frédéric Marin of the Université de Strasbourg, published in 2021, suggested that depending on voyage duration and survival assumptions, populations of several hundred might be preferable to minimize the risk of genetic collapse. Every answer generates a new question. The ship must be larger to accommodate a larger population. A larger ship requires more propellant to accelerate. More propellant means more mass, which requires more propellant still. The Tsiolkovsky equation imposing itself again, recursive and relentless. The universe does not grant exemptions from its mathematics. Stop here for a moment, because something important is about to arrive. Throughout this entire journey, from the heliopause to Sirius, through the catalogue of red dwarfs, through the radiation and the bone loss and the multi-generational psychology, we have been framing the problem in a particular way. We have been asking, what would it take to send a human being, as presently constituted, across the interstellar void? What shielding? What propulsion? What life support? What genetic planning? What psychological preparation? This framing contains an assumption so embedded that it is almost invisible. The assumption is that the traveler who departs is the traveler who arrives. That the body being sent is the body that lands, perhaps aged, perhaps changed, but fundamentally continuous with itself. What happens when that assumption is removed? Consider. If the crossing takes 4 centuries, the crew who arrives at Proxima Centauri is not the crew who departed Earth. It is their distant descendants, born in a steel cylinder in the dark between stars. In what sense are they still representatives of Earth? In what sense do they still carry the mandate, the mission, the values of the civilization that built their great-grandparents' ship? Civilizations change dramatically in the 4 centuries. In the 4 centuries between 1620 and 2020, human civilization went from wooden ships and handset type to nuclear reactors and genetic sequencing. The people who arrived at Proxima Centauri after a 4-century crossing would arrive as a separate culture, not a diaspora from Earth, but a new thing, shaped by an experience no earthly culture had undergone. And this is where the entire question of interstellar travel inverts. Once you see it, the previous framing collapses. The question was never really, can we build a fast enough ship? The question underneath that engineering question is, what are we willing to become in order to go? Is the answer biological transformation, genetic engineering, radical life extension, the deliberate modification of human physiology to withstand cosmic radiation and endure centuries of crossing? Some researchers in astrobiology and bioethics have begun asking these questions seriously. If the crossing requires that you no longer be quite human in the biological sense, does the word human apply to what arrives? Is the answer uploading, transferring the patterns of consciousness into digital form, transmitting them as signals, reconstructing them at the destination? This is not a technology that exists or whose physical feasibility is even established, but it eliminates the biology problem entirely. It also eliminates the question of continuity entirely. Is a reconstructed digital pattern the same person who was encoded? We do not know. We cannot know, not because the instruments are insufficient, but because the question may not have an answer that physics can provide. Is the answer sending machines entirely? No biology, no consciousness, only autonomous robotic probes capable of exploration and data transmission. This avoids every biological obstacle. It answers none of the deeper questions about what crossing the interstellar void means to a civilization with consciousness and longing. What is the destination worth if not being capable of experiencing it arrives? What does it mean to reach another star if the beings who reach it have been so transformed by the crossing that they bear no meaningful continuity with the beings who dreamed of going? Can a civilization outlast its own technology? Or does technology, in advancing toward the speed required for interstellar travel, inevitably outpace the biology that built it? What happens to a species that dreams of the stars but exists on timescales thousands of times shorter than the timescales required to reach them? If any other technological civilization in the galaxy has solved this problem, and the Fermi paradox, the silence of the radio sky, suggests either that none have, or that they have solved it in ways we cannot detect. What did they have to become in order to solve it? And here is the question that sits beneath all the others, the one that does not yield to engineering analysis or biological modeling. What does it mean that the universe is structured this way? That conscious beings capable of understanding cosmic distances, capable of doing the mathematics, capable of building the telescopes and the probes and the equations, are confined by their biology and their timescales to the surface of a single planet? Is this a solvable problem, or is it a permanent condition? We cannot know whether consciousness can survive interstellar transit in any form we would recognize as continuous with its origins. That epistemological limit is genuine, and it is not merely the limit of current technology. It is a limit rooted in the deepest uncertainties about what consciousness is, how it relates to physical continuity, and whether identity survives transformation. At the scale the crossing demands, these are not questions physics alone can answer. Once you sit with this long enough, the entire picture changes. The subject of interstellar travel was never simply a propulsion engineering problem. It was always a philosophy problem wearing engineering clothes. The galaxies are full of stars. The stars are full of physics, and somewhere between the dream and the crossing lies a territory that no equation has mapped, the territory of what we must become or surrender to reach them. Picture yourself standing outside on a clear night, far from any city, in a place where the darkness is complete. Perhaps you are standing on a hilltop somewhere in the southern hemisphere, in the Atacama Desert of Chile, where the air is so dry and thin that the sky looks almost three-dimensional, the stars not points but presences, hanging at different depths, the Milky Way a river of light so dense it casts a faint shadow. The constellations of the southern sky wheel slowly overhead. Somewhere in the constellation Centaurus, there is a bright point. Two bright points, actually, merged to the naked eye. That is Alpha Centauri. And nearby, invisible to you, orbiting that pair at immense separation, is a faint red dwarf that you cannot see without a telescope. And around that faint red dwarf, there is a planet. And around that planet, there is an atmosphere. Or perhaps not. And on the surface of that planet, there is something, or perhaps nothing. You cannot see any of it. You see only the point of light. This is worth dwelling on, not as a failure of perception, but as a fact about what it means to be here, in a human body, on the surface of this particular planet, looking outward. Everything we have explored in the past several hours of this journey, the heliosphere, the interstellar medium, the local bubble, the catalogue of red dwarfs, the radiation environment, the bone loss, the propulsion equations, the multi-generational ship problem, the question of what we must become in order to go. All of it was extracted from that single point of light and the mathematics we applied to it. Human beings looked at a dot and read from it the temperature of a stellar atmosphere, the mass of an orbiting planet, the history of a white dwarf, the rate of atmospheric stripping by ultraviolet radiation. We looked at dots and extracted a universe. That capacity to reach across distances that we could never physically cross with instruments sensitive enough to read the light is itself one of the most extraordinary things in the known universe. And it is easy to overlook because it has become routine. The press releases from observatories no longer make headlines the way they once did. Another exoplanet, another stellar spectrum, another measurement of a stellar wind. These things arrive in the scientific literature with the quiet regularity of the mail, and we absorb them and move on. But stop for a moment and feel what they represent. The light reaching Earth from Proxima Centauri tonight left the star 4.244 years ago. It crossed 40 trillion kilometers of interstellar medium, through the cold neutral phase, through the hot ionized plasma of the local bubble, through the wispy outer edges of the heliosphere, and arrived at a telescope mirror that was polished to within a fraction of a wavelength of light, focused by instruments designed to split it into its component frequencies, and analyzed by software that compared its absorption lines to laboratory measurements of known elements. From that analysis, we know the star's temperature. We know its composition. We know its mass, its age, its magnetic activity cycle, the approximate orbit of its planet. We know more about Proxima Centauri, sitting motionless in a building on Earth, than any explorer in human history knew about a destination before they departed for it. The journey we have been taking is a journey made of light and mathematics. It is not lesser for that. In some ways, it is more intimate than any physical crossing could be, because it reaches not just to the surfaces of things, but into their physics, their history, their future. Physical crossing would tell you what Proxima Centauri looks like from close-up. Light and mathematics tell you what it is. Rest here for a moment with that. The two Voyager probes are still out there, moving through the interstellar medium in their separate directions, their signals arriving on Earth as whispers barely distinguishable from noise, their plutonium batteries cooling toward the temperature of the space around them. Voyager 1, somewhere beyond the heliopause in the direction of Ophiuchus. Voyager 2, farther south, having crossed its own boundary in 2018. Both of them are surrounded now by interstellar gas, the same hydrogen and helium and dust that fills the space we have been crossing in imagination. They are genuinely there, in the medium, measuring it in real time, their instruments touching the material we have been describing with words. They will not stop. That is perhaps the most haunting thing about them. There is no mechanism to decelerate them, no signal we will send that could break their passage. In 40,000 years, Voyager 1 will pass within 1.6 light-years of a star called Gliese 445. In 296,000 years, Voyager 2 will pass within 4.3 light-years of a star called Ross 248. Neither probe will be detected by any civilization at those stars, if any civilization exists there. The signals will have died centuries before. The probes will pass in silence, two small artifacts of a species that may have long since transformed or ended, carrying records of music and greetings and the sounds of surf and wind that may never be heard again by anyone. It could have been otherwise. We could have built slower probes, and they might have drifted differently. They could have been built differently, aimed differently, powered differently. Instead, they were built exactly as they were, in exactly the years they were, and they travel in exactly the directions they do. The universe, indifferent, does not revise. The interstellar medium through which they move has been flowing slowly in its various phases for billions of years. The local bubble's walls, the cold, dense shells of interstellar gas compressed by supernova blast waves 10 or 20 million years ago, are still expanding, still cooling, still slowly reshaping the local stellar neighborhood. The dust grains drifting through the medium, silicates and carbon compounds, fractions of a micrometer across, are remnants of the stellar winds and supernova ejecta of stars that lived and died before our sun formed. They have been drifting for billions of years. They will drift for billions more. Our sun, our Earth, our bodies are made of the same kinds of material. The same supernovae that scattered dust into the early galaxy also built the molecular cloud that collapsed to form the solar system. We are made of interstellar medium. We are made of the very substance we have been crossing. Somewhere in that same medium, at a distance of 4.244 light-years, the red fire of Proxima Centauri burns on, unaware of its observers. Its flares pulse into the space around it in irregular bursts. Its planet, if it has an atmosphere, is being battered by radiation, cycling through its 11-day orbit in the dim, ruddy light, one face always turned toward the star, one face in permanent night. Whatever is on that planet, rock, ice, nothing, something we have not imagined, it has been there for billions of years, longer than complex life has existed on Earth, longer than our genus has existed. It is patient in the way that rocks are patient, in the way that stars are patient, which is to say that patience and impatience are both categories that belong to minds, and the rock and the star have no mind. Only we have the mind. Only we feel the distance. Anaphora for the dark, for the medium, for mathematics. The distance is real. The distance is measured. The distance is, in its way, a gift, because it is the distance that makes the looking meaningful. A universe in which the nearest star was around the corner would not require what this one requires of us. It would not ask us to develop the patience, the precision, the accumulated collaborative effort of generations of astronomers making measurements in cold observatories in the middle of the night. It would not ask us to become the kind of species that can know a place without going there. The difficulty is not incidental to the meaning. The difficulty is the meaning. And now the cooling settles, and something that has been building throughout this entire journey arrives at last. There is a moment in the study of ancient navigation that stops you cold if you let it. Sometime around the year 1000 CE, possibly earlier, the dating is uncertain, a group of Polynesian navigators set out in double-hulled canoes from the Society Islands or the Marquesas, sailing north-northeast into the open Pacific Ocean. They had no compass. They had no sextant. They had no charts of the destination, because no chart of the destination existed. No one from their culture had been there. They navigated by the stars, by the shape of the swells under the hull, by the flight patterns of birds, by the color of the water. They were crossing open ocean for roughly 3,700 kilometers, aiming for a group of islands, the Hawaiian archipelago, that they knew existed only from the direction birds had come from the pattern of clouds on the horizon that suggested distant land, from whatever oral traditions or navigational memory pointed them northward. They found it. They crossed 3,700 kilometers of open Pacific, without instruments, without the ability to communicate with home, in vessels that would fit inside a modern living room, and they arrived at a destination they had never seen. The Polynesians did this repeatedly, Samoa to Fiji, Tonga to New Zealand, the Society Islands to Hawaii and back, building the most extensive maritime civilization in human history, spanning a third of the globe's surface, one impossible crossing at a time. Now hold that image alongside the image of an interstellar crossing. There are differences, of course, and they are not trivial. The Pacific Ocean is not a light year wide. The canoes carried living people who completed the crossing in weeks rather than centuries. The birds and the swells provided navigational feedback that interstellar space will not provide. These differences are real. They are not being minimized. But something in the structure of what the Polynesian navigators did is relevant here. They crossed a distance that, from the perspective of any earlier culture in any earlier epoch, would have been considered absolutely, categorically impossible. The Mediterranean sailors of antiquity did not sail the open ocean. The Viking longships, magnificent and brave, hugged coastlines where they could cross the North Atlantic, only where island stepping stones, the Faroes, Iceland, Greenland, made the crossing incremental. The open Pacific, trackless and vast, was a genuine void, and the Polynesians crossed it, not because they had instruments sufficient to the task, but because they developed the understanding, the patience, and the accumulated knowledge of the ocean's behavior that made the instruments unnecessary. What they had, fundamentally, was the right kind of knowing. Not the knowing of charts and compasses, but the knowing of swells and stars and birds, a knowledge built across generations, refined across thousands of crossings on shorter routes, scaled eventually to the impossible. The question that the history of interstellar propulsion keeps raising, and that the history of the Polynesian voyages illuminates, is not whether the crossing is possible. It is what kind of knowledge is required, and whether we are the generation that builds it, or the generation before the generation that builds it, or many generations before that. Every crossing of an impossible distance in human history began as an act of imagination before it became an act of engineering. Someone looked at the open water and decided, on evidence that was insufficient by any rational accounting, that there was land beyond the horizon. Someone looked at the stars and decided, on the basis of mathematics that had never been tested at the required scale, that those points of light were suns at enormous distances. Someone looked at the equations of special relativity and decided, on theoretical grounds alone, that time dilates at near light speed in ways that might make the crossing survivable for the traveler, even if not for those left behind. The imagination preceded the capability by decades, by centuries, by millennia. Return now to the opening image. Someone, on an ordinary afternoon in human history, perhaps in antiquity, standing on the banks of the Nile watching Sirius rise before dawn, perhaps in the 17th century, peering through one of the first telescopes at the blurred disk of a star, decided that the stars were reachable. The math in their time was not available to tell them otherwise. The math in their time was not available at all. They decided purely on the basis of longing, and longing, it turns out, has been the first instrument of every great crossing. The math does tell us otherwise. We have done the math in considerable detail in this journey. We have calculated the travel times and the radiation doses, and the fuel requirements, and the genetic diversity thresholds, and the communication delays. The math is honest, and it is not encouraging. The nearest star is 4.244 light-years away, and every vehicle we have ever built would take tens of thousands of years to reach it. And every propulsion concept advanced enough to reduce that to human timescales requires engineering that does not exist, and the human body was not designed for the crossing in any form we have yet imagined. But the math also does not tell us it is impossible. It tells us it is very, very hard. And very, very hard is not the same as impossible. It never has been. What does it mean, then, that we cannot know whether it will be done? Not that we do not yet know, but that the question sits in a zone of genuine epistemic uncertainty that extends beyond our predictive horizon. Whether humanity will, in 10,000 years, or 100,000 years, or 1,000,000 years, cross the interstellar gulf in some form, biological, digital, hybrid, transformed beyond current recognition, cannot be determined from where we stand. The future of a species across timescales of that magnitude is not something physics can calculate. Too many contingencies intervene: extinction risks, technological trajectories, political decisions, changes in values, the possibility of contact with other technological civilizations, the possibility of fundamental discoveries that rewrite the constraint equations entirely. We cannot know, and there is something important in that admission. The cannot is not a failure of nerve. It is a recognition of the actual structure of uncertainty at civilizational timescales. Human beings have been in their current anatomical form for perhaps 300,000 years. The first evidence of symbolic thought and long-distance trade in materials dates from perhaps 100,000 to 150,000 years ago. Writing is 5,000 years old. The telescope is 400 years old. The concept that other stars might have planets, a concept so obvious to us now that it feels like common sense, was vigorously debated as recently as the mid-20th century. We have been asking serious, empirically grounded questions about interstellar travel for perhaps 50 years. We do not know what questions will seem obvious in 50,000 years, in 500,000 years, in 5,000,000 years, if anyone or anything descended from us is around to ask them. What we can say with confidence is this: the act of asking the question matters. The act of measuring the distance, calculating the dose, modeling the atmosphere of Proxima b, designing the light sail, running the Mars 500 simulation, listening for signals from other stars, all of it matters. Not only because it might eventually lead somewhere engineeringly useful, but because it is the practice of a species trying to understand its position in a universe far larger than it was built to comprehend. Consider the Egyptian astronomer priests, who calibrated their calendar to the rising of Sirius. They did not know Sirius was 8.6 light-years away. They did not know it was a binary system with a white dwarf companion. They did not know it was an A-type main sequence star with a surface temperature of 9,940 Kelvin. They knew that it rose before dawn in late July, and that the Nile flooded, and that the planting season followed, and that civilization depended on this rhythm. They wove a point of light 8.6 light-years away into their agricultural cycle that fed a civilization for 3,000 years. They understood Sirius in the way available to them, with a depth of attention that shaped the lives of millions. Friedrich Bessel, in 1838, made the first measurement of a stellar distance, and what he found was not comfort, but abyss. The stars were not in a crystalline sphere just overhead. They were at distances so vast that light, which had seemed up to that point effectively instantaneous, needed years to cross. Bessel understood what this meant. The universe had become unimaginably large in the space of a single calculation. He did not despair. He published his measurement. He continued his work. He went on to detect the wobble in Sirius's proper motion that Alvan Graham Clark would confirm as a white dwarf companion 6 years after Bessel's death. The abyss did not stop him. It informed him. Guillaume Anglada Escudé, in 2016, announced the planet at Proxima Centauri. He had spent years gathering radial velocity data from multiple observatories, fighting the noise of stellar activity in his measurements, refining his analysis until the signal was undeniable. What he found was not a comfortable world. It was an uncertain, radiation-battered, possibly atmosphereless rock orbiting a violent red dwarf in a tight, tidally locked orbit. He announced it anyway, because uncertainty is not the same as absence, because the possibility matters as much as the confirmation, because the act of looking, of measuring, of publishing what you find honestly, including the uncertainty, is how the picture gets built, one careful measurement at a time. The stars are not reachable today. They may not be reachable for a very long time. They may be reached in a form so transformed that the beings who reach them would barely recognize the beings who dreamed of going. The crossing, if it ever happens, will be one of the most consequential and difficult things any civilization in this galaxy has ever attempted. It will require propulsion physics that does not yet exist, materials science that is in its infancy, biological adaptation or transformation at a scale that raises philosophical questions we have barely begun to ask, and a continuity of purpose across timescales that no human institution has ever maintained. All of that is true. It could have arrived earlier. It could have been discovered later. It could have turned out that we were the only conscious beings in the galaxy, in which case the impulse to cross the void would carry a weight that is almost unbearable to contemplate. It could have turned out that the nearby stars are rich with habitable worlds, teeming with life, making the crossing urgent and the destination welcoming. Instead, the universe arranged itself as it did. A few warm, dim, violent stars nearby, a gulf of extraordinary hostility between, and a species on one blue planet with the mathematics to understand the situation and the longing to be somewhere other than where it is. That longing is not a flaw. It is not a mistake of evolution, not an evolutionary byproduct to be managed or suppressed. It is the thing that makes the looking possible. Without the longing, no one builds the telescope. Without the longing, Bessel does not spend years at the heliometer. Without the longing, The Polynesians paddled to the edge of the known Pacific and turned back. The longing is the instrument. It always has been. Proxima Centauri burns on, 4.244 light-years away, indifferent and ancient. Its planet completes another orbit in 11.2 days, with or without an atmosphere, habitable or not, watched by no one on its surface and barely watched by anyone on ours. The interstellar medium drifts slowly between, threaded with radiation and dust, and the magnetic memory of long-dead supernova. The two Voyager probes move outward in their separate directions, silent and patient, carrying the golden records of a species that may or may not still exist when those records next encounter anything capable of reading them. And on an ordinary evening on Earth, someone is standing outside in the dark, looking up, feeling the distance in the way that only a conscious being in a universe this large can feel a distance, as an ache, as a question, as the beginning of something that has not yet been named. The journey is over now, in the sense that all imagined journeys eventually return to the place they began. Stand back on Earth for a moment. Feel the ground under you. Feel the air, thick, warm, full of nitrogen and oxygen, and the traces of 1 billion years of biological chemistry. Feel the weight of a full atmosphere pressing down on your shoulders, invisible and constant and life-giving. This is what you would miss first if you left. This is what no starship has yet found at any of the addresses we visited with any certainty. We traveled outward from the last warm boundary of our solar system, the heliopause, where Voyager 1 crossed into interstellar space in 2012, confirmed by Edward Stone and his team, and found not emptiness, but a structured, complex, radiation-filled medium that has been flowing slowly between the stars since long before our sun ignited. We crossed the local bubble, a vast cavity in the interstellar medium carved by supernovae 10 to 20 million years ago. Its hot ionized plasma threading our path with magnetic fields and galactic cosmic rays that no heliospheric shield deflects. We arrived at Proxima Centauri, that dim red fire 4.244 light-years from Earth, and found a star of extraordinary longevity and extraordinary violence. A flare star that bombards its surroundings with UV bursts capable of stripping planetary atmospheres at rates 10,000 times faster than the Sun strips Earth's, as Catherine Garcia Sage and her colleagues showed in 2017. We found its planet, confirmed in 2016 by Guillem Anglada Escudé and his team, orbiting in 11 days, possibly tidally locked, possibly atmosphereless, possibly an opportunity, and possibly a barren rock. And we understood that the word possibly is doing enormous work in that sentence. We moved outward to Alpha Centauri A and B, those two sun-like stars in the closest bright stellar system. The ones Thomas Henderson measured from South Africa in the early 1830s, whose distances he hesitated to publish out of fear of disbelief. We found them brilliant and familiar, their light recognizable in color and character, their planetary systems hidden from our instruments by the very proximity that makes them our nearest sun-like neighbors. We traveled to Barnard's Star, that ancient, slowly rotating red dwarf moving faster across our sky than any other known star, moving with such haste relative to the Sun that Peter van de Kamp spent decades convinced he had detected planets tugging at its path, planets that turned out to be ghosts in the instrumentation, a reminder that the desire to find something can shape what the data appears to show. We passed Wolf 359, barely above the threshold of stellar ignition, a dim orange ember that will outlast our sun by factors of hundreds. And we arrived at Sirius, brilliant, blue-white, ancient in human culture and young in cosmic terms, carrying in its system the compressed remnant of a star that burned itself out 120 million years ago, a white dwarf the size of Earth and the mass of the Sun, cooling in silence for geological epochs. At every stop, the same pattern: distance, hostility, uncertainty, beauty. We turned eventually from the stars themselves to the body that would have to cross to them. We found a body designed for a specific gravity, a specific magnetic shielding, a specific radiation environment, a body that begins to fail within months in the conditions of even low Earth orbit, that loses bone and muscle and visual acuity and immune function on timescales that make years-long crossings dangerous and centuries-long crossings biologically catastrophic. We found a radiation environment in interstellar space that no practical shielding design has yet solved, a cosmic ray flux that penetrates all conventional barriers and that accumulates damage in DNA and neural tissue across the timescales relevant to any credible interstellar mission. We found multi-generational mathematics, the genetic diversity thresholds, the psychological isolation, the cultural transformation that 4 centuries of crossing would impose on any founding crew, such that the beings who arrived would barely recognize themselves as descendants of the beings who departed. And we found, underneath all the engineering and biology, the deeper question: not whether we can build a fast enough ship, but what we are willing to become in order to go. Whether the being that crosses is still continuous with the being that dreamed of crossing. Whether the crossing requires transformation at a scale that makes the words human and arrival philosophically uncertain in ways that physics alone cannot resolve. The 4 questions planted at the beginning of this journey have all received answers now, of a kind. The interstellar medium is not empty. It is structured, tenuous, radiation-threaded, hostile at speed, threaded with magnetic fields and the dust of dead stars. Proxima Centauri b may or may not be habitable. The current evidence leans toward difficulty, toward atmospheric loss, toward a world shaped by violence rather than gentleness. But the question is genuinely open. The journey would devastate the human body as presently constituted. This is not speculation, but physiology, measured carefully in orbit and in isolation chambers, and in the mathematics of accumulated radiation dose. And the grand question, the one that sat in the hallway with the door ajar throughout: will we ever go? Here is the answer, such as it is. We do not know. We cannot know. Not from where we stand, not on the timescales available to us, not with the predictive reach available to any species 4 centuries into the scientific method. What we can say is that every impossible crossing in the history of our species began with the same insufficiency: instruments not adequate to the task, knowledge not yet sufficient, engineering not yet imagined. And that some of those crossings were made anyway, eventually, by beings who built the knowledge and the instruments and the engineering across generations, one careful step at a time. And we can say that the longing to cross, the specific ache of looking at a point of light and wanting to know what surrounds it up close, is not a mistake. It is the motive force behind every telescope, every space mission, every late-night calculation in a cold observatory. Friedrich Bessel looked at a star for years and found the abyss. He published it anyway. Jan Oort looked at the orbits of comets and deduced a halo of icy bodies no instrument had ever seen. He published it anyway. Guillaume Anglada Escudé spent years fighting stellar noise in radial velocity data until a small, uncertain, possibly atmosphereless planet emerged from the signal. He published it anyway. Each of them looked into the distance, found it more vast and more difficult than expected, and returned to their instruments. The distance did not discourage the looking. In some sense, that is difficult to articulate, but easy to feel. The distance made the looking more necessary. The stars we visited are still out there, burning or cooling on their own timescales. Proxima Centauri will still be burning when our sun has expanded into a red giant and consumed the inner planets. Barnard's star was ancient before Earth existed. Sirius B has been cooling since before the dinosaurs ended. The interstellar medium drifts unchanged between them, its hydrogen and helium and silicate dust grains indifferent to the passage of a species that has been asking questions about it for a few hundred years. The Voyager probes move outward in their separate directions, carrying their golden records into a darkness they will cross for millions of years without arriving anywhere. They are already farther from home than any human artifact has ever been. They are still unimaginably close. Somewhere in the constellation Centaurus, a point of light that has been called Rigil Kentaurus, and Alpha Centauri, and the southern pointer holds its position in the sky above the southern hemisphere. It has been there, visible, since human beings first stood upright in Africa and looked south at the night sky. It has been there for every generation since. It will be there for every generation ahead, through whatever transformations or extinctions those generations contain. It could have been otherwise. The nearest star could have been farther. The interstellar medium could have been denser, or the radiation more extreme, or the physics of propulsion even less yielding. It could have been that no nearby stars had planets at all, that the catalogue was empty of even uncertain possibilities. Instead, the universe arranged what it arranged, a small, violent red dwarf at 4 light-years, with a planet in the right zone and the wrong radiation environment, orbited by uncertainty and hope in roughly equal measure, visible to instruments built by a species that has been wondering about it for less time than the planet has been battered by its star's flares. The distance between us and the nearest star is the most important physical fact about our situation. It is the fact that makes us, in a real and measurable sense, alone. Not philosophically alone, not emotionally alone, but physically, practically, cosmically alone, in a way that may never be resolved in the lifetime of our civilization. It is also the fact that makes the reaching meaningful. A universe without that distance would not require what this one requires: the patience, the precision, the multi-generational accumulation of careful observation, the willingness to build instruments for questions whose answers will arrive after your death, the capacity to love a point of light you will never visit. 40 trillion kilometers away, on an ordinary night that has lasted 4 billion years, a dim red star burns in the dark. Its planet turns, one face in light and one in shadow. The light reaching Earth from that star tonight left it 4.244 years ago. It has crossed the interstellar medium, the heliosphere, the atmosphere, and arrived here, at your eye, or at a mirror, or at nothing at all if no one is looking. The looking matters, the measuring matters. The dreaming, which always precedes engineering by centuries, matters. If this changed how you think about the stars and the distances between them, about what it means to look up and feel the light of another sun on your face, then the time was well spent. Thank you for staying. Thank you for crossing this distance in the only way any of us have managed so far, with attention, with patience, and with the quiet willingness to sit with questions that do not resolve quickly in the dark, looking outward.